Hello, dear wanderer. Welcome back to the Midnight Explorer. Tonight, I want you to find somewhere comfortable, somewhere quiet, perhaps near a window where you can see the sky, or maybe just a corner of your room where the world feels a little softer, a little more still. Take a breath with me, deep and slow. Tonight, we're going to look up. We're going to remember something we've almost forgotten in our busy, bright, electric world. Tonight, we're going to rediscover the night sky, not just as a canvas of distant stars, but as the very thing that shaped us, that taught us to wonder, to question, to dream. For thousands of years, long before screens lit up our faces, the night sky was humanity's first book, first teacher, first companion in the darkness. It told us when to plant our crops, when to prepare for winter, how to navigate across endless oceans. It gave birth to our myths, our mathematics, our understanding of time itself. But more than that, it made us feel small in the most beautiful way. It reminded us that we are part of something vast, something ancient, something utterly mysterious. So settle in. Let the day fall away. And let me tell you the story of the night sky and the people who looked up, wondered, and changed everything. Close your eyes for a moment and imagine this with me. Imagine you are alive 40,000 years ago. There are no cities, no electric lights, no phones buzzing in your pocket, no alarm clocks waiting to shatter your morning. You live in a world of firelight and shadow, of animal sounds in the dark forest, of wind moving through grass like breathing. And every single night, without fail, the sky opens above you. Not the pale, washed-out sky we know today, dimmed by the glow of a million streetlights and car headlamps and shopping centers that stay lit all night long. No, this sky is different. This sky is alive. When the sun sets, it doesn't just get dark. The darkness reveals. As your eyes adjust, more and more stars appear. First dozens, then hundreds, then thousands upon thousands. The Milky Way, our home galaxy, stretches across the heavens like a river of light, so bright you could almost read by it, so thick with stars it looks like spilled milk across black silk. This is the sky your ancestors knew. This is the sky that shaped human consciousness for most of our existence as a species. The questions begin. Now imagine you are sitting by your fire. Your family is nearby, your partner, your children, your parents, if you're lucky enough that they've survived into old age. The fire crackles, someone tells a story, someone else repairs a tool by firelight. And you look up. You've looked up 1,000 times before, you'll look up 1,000 times more. But tonight something shifts in your mind. Tonight you begin to wonder. What are those lights? Why do they move across the sky in patterns? Why do some of them wander while others stay fixed in place? Why does the moon change shape? Why does the sun return each morning? These seem like simple questions to us now. We learn the answers in school, often before we're old enough to truly appreciate the mystery. But for your ancient ancestor, sitting by that fire, these questions were profound. They were urgent. They touched on survival itself. Because the sky wasn't just pretty. It was practical. It was a calendar. It was a map. It was a clock. When certain stars appeared on the horizon at dawn, it meant the floods were coming. When the moon reached a certain phase, it meant the tides would be high. When that bright cluster of stars, the Pleiades, vanished in spring and reappeared in autumn, it marked the seasons for planting and harvest. If you couldn't read the sky, you couldn't survive. Cave paintings and cosmic maps. In 1940, in the Dordogne region of France, 4 teenagers and a dog stumbled upon something extraordinary. Deep in a cave system near the village of Montignac, They found walls covered with ancient paintings. Paintings of horses and bulls and deer rendered in ochre and charcoal with stunning beauty and precision. This was Lascaux Cave, and those paintings were about 17,000 years old. But here's what captured the imagination of later researchers. Among those animals, there were patterns of dots, clusters of marks that seemed too deliberate to be random. Some archaeologists believe these dot patterns represent constellations, maps of the night sky, painted by Paleolithic artists who wanted to record what they saw above them. We can't know for certain. These people left no written records, no explanations, but the possibility is tantalizing. Imagine an artist, perhaps a shaman or a storyteller, perhaps just someone with a gift for observation and memory, standing in the firelit cave and recreating the patterns of stars they'd memorized, teaching the next generation, preserving knowledge, making the invisible visible. This is one of humanity's first impulses, to make marks, to record, to remember the sky. The Mesopotamians, first scientists of the stars. Now let's move forward in time and south and east to the land between two rivers, the Tigris and Euphrates, the land we now call Iraq. The ancient Greeks called it Mesopotamia, meaning between rivers. Around 5,000 years ago, something remarkable was happening here. Human beings were inventing civilization as we know it. They were building cities, developing agriculture on a large scale, creating the first written languages, and they were watching the sky with unprecedented dedication. The Mesopotamians, the Sumerians, the Babylonians, the Assyrians, were meticulous observers. They built tall towers called ziggurats, not just as temples, but as observatories. Priests would climb to the top and spend entire nights recording the movements of celestial bodies. Why? Because they believed the gods spoke through the heavens. Every unusual occurrence in the sky, a comet, an eclipse, the appearance of a bright new star, was an omen. It predicted the fate of kings, the outcome of battles, the prosperity of the harvest. This might sound like superstition to modern ears, and in some ways it was. But it was also the beginning of systematic astronomy. Because to predict omens, you first had to understand patterns. You had to keep records. You had to recognize that the sky wasn't random. It moved according to rules. The same constellations appeared in the same seasons, year after year. The moon cycled through its phases in a predictable rhythm. The planets wandered across the zodiac in patterns that could be tracked and anticipated. The Babylonians kept astronomical records for centuries. They developed sophisticated mathematical techniques to predict eclipses. They divided the sky into 12 sections, the signs of the zodiac, that corresponded to the sun's path through the year. They calculated the length of the lunar month to within a fraction of a second of the modern measurement. They were doing science, even if they called it divination. The Egyptian sky, gods, and geometry. Meanwhile, along the Nile River, another great civilization was looking up and seeing something different. The ancient Egyptians saw the sky as a realm of the gods. The sun was Ra, the supreme deity who sailed across the heavens in his golden boat each day, then traveled through the underworld each night to be reborn at dawn. The stars were souls of the dead, particularly the pharaohs, who ascended to the sky to live eternally. But Egyptian astronomy was also deeply practical. The entire rhythm of Egyptian life depended on the Nile River's annual flood. Every year, like clockwork, the river would overflow its banks, depositing rich, fertile silt across the farmlands. This flood made Egypt the breadbasket of the ancient world. But if you couldn't predict when it would come, you couldn't prepare. You couldn't clear the fields in time, couldn't move your livestock to safety, couldn't plan the planting season. So, the Egyptians watched the sky. They noticed that just before the flood season began, a particular star would appear on the eastern horizon just before sunrise, after being invisible for many weeks. This star was so important to Egyptian life that they named it Sopdet. The Greeks later called it Sothis. We know it today as Sirius, the brightest star in our night sky. The heliacal rising of Sirius, that first moment when it became visible again after its absence, marked the Egyptian New Year. It was the signal that the flood was coming, and it was so reliable that the Egyptians based their entire calendar on it. They also aligned their monuments with the sky. The Great Pyramid of Giza, built around 4,500 years ago, is aligned to the cardinal directions with astonishing precision. Its sides face north, south, east, and west to within a fraction of a degree. Some of its internal shafts point toward specific stars that were significant in Egyptian cosmology. The Egyptians weren't just building tombs, they were building bridges between earth and sky, between mortality and eternity. The Greek Revolution, asking why. But it was in ancient Greece, starting around 2,600 years ago, that something fundamentally shifted in how humans thought about the sky. The Greeks inherited astronomical knowledge from the Egyptians and Babylonians. They knew the constellations, could predict eclipses, understood the cycles of the seasons. But Greek philosophers began asking a different kind of question. They didn't just want to know what happened in the sky, they wanted to know why. They wanted to understand the underlying principles, the causes, the fundamental nature of the cosmos. Thales of Miletus, one of the first Greek philosophers, proposed that natural phenomena had natural explanations, not just the whims of gods. He reportedly predicted a solar eclipse in 585 BCE, an achievement that demonstrated the power of observation and reasoning. Pythagoras and his followers believed that the universe was governed by mathematical harmony. They thought the planets moved in perfect circles and produced a music of the spheres, a cosmic symphony inaudible to human ears but mathematically perfect. Aristotle constructed an entire cosmology, placing Earth at the center of the universe, with the moon, sun, planets, and stars arranged in concentric spheres around it. It was wrong, as we now know, but it was systematic. It attempted to explain everything in the sky with a single coherent theory. And then there was Aristarchus of Samos, who around 270 BCE proposed something radical. What if the Earth wasn't the center of everything? What if we orbited the sun? He was ignored. His idea seemed absurd. If Earth moved, wouldn't we feel it? Wouldn't birds be left behind in the air? Wouldn't everything fly off the surface? It would take another 1,800 years before his insight was rediscovered. The gift of curiosity. What I want you to feel as we move through this ancient history is not just the accumulation of facts. What I want you to feel is the wonder that drove these observations. These were people not so different from you and me. They felt love and fear, hunger and joy. They worried about their children, mourned their dead, told jokes by firelight, and dreamed of the future. But they also looked up. They paid attention. They noticed patterns. They asked questions. They tried to understand. And slowly, generation by generation, they learned to read the sky. They learned that the world was governed by patterns, not chaos, that the universe could be understood, not just feared, that human minds could grasp the mechanics of the cosmos, could predict the future movements of celestial bodies, could navigate by starlight across unknown seas. This was revolutionary. This was the birth of science itself. And it all started with the simple act of looking up at the night sky and asking, what is that? Why does it move that way? What does it mean? The Egyptian sky, gods and geometry. The Roman Empire fell. The classical world with its libraries and academies and philosophical schools crumbled. Europe entered what historians once called the Dark Ages, though that term really isn't fair. Learning didn't disappear, it just moved elsewhere. In medieval Europe, astronomy became the domain of monasteries and universities. Monks studied the sky to calculate the dates of religious festivals, especially Easter, which had to be properly aligned with both the lunar and solar calendars. They preserved some ancient texts, copied them by hand in candlelit scriptoriums, passed them down through generations. But the cutting edge of astronomy, the place where new discoveries were being made, was no longer in Europe. It was in the Islamic world, the golden age of Islamic astronomy. While Europe struggled through political fragmentation and economic collapse, a new civilization was rising in the Middle East, North Africa, and Spain. The Islamic caliphates, starting in the 7th century CE, created a vast empire that valued learning, translation, and scientific inquiry. The Abbasid caliphs in Baghdad, particularly during the 8th and 9th centuries, gathered scholars from across the known world. They translated ancient Greek, Persian, and Indian texts into Arabic. They built observatories, libraries, and centers of learning. And they made astronomy into a sophisticated mathematical science. One of the greatest was al-Battani, who lived in the late 8th and early 9th centuries. He spent decades making precise observations of the sun, moon, and planets. He calculated the length of the solar year to within minutes of the modern value. He improved on Ptolemy's astronomical tables, correcting errors that had persisted for centuries. He developed trigonometric methods that would influence mathematics for generations. Then there was Al-Sufi, who in 964 CE compiled the Book of Fixed Stars, a comprehensive catalog of over 1,000 stars with descriptions of their brightness, color, and position. He was the first astronomer to observe the Andromeda galaxy, which he described as a little cloud. He corrected numerous errors in earlier star catalogs and added his own original observations. Ibn al-Haytham, known in the West as Al-Hazan, revolutionized not just astronomy but the entire scientific method. In the early 11th century, he wrote about light, optics, and vision with such rigor and experimental precision that he sometimes called the father of modern optics. He questioned everything, tested hypotheses, and insisted on empirical evidence. Truth is sought for itself, and those who are engaged upon the quest for anything for its own sake are not interested in other things. Finding the truth is difficult, and the road to it is rough. These weren't just scholars preserving old knowledge, they were making new discoveries, developing new instruments, creating new mathematical techniques. They built astrolabes, sophisticated devices that could solve complex astronomical problems, calculate prayer times, determine the Qibla, the direction to Mecca, and navigate by the stars. When you hear that Arabic names dominate our star maps, Aldebaran, Betelgeuse, Rigel, Altair, Deneb, you're hearing an echo of this golden age when Islamic astronomers named and cataloged the heavens. China's celestial bureaucracy. Meanwhile, on the other side of the world, Chinese astronomers were maintaining the longest continuous astronomical record in human history. For over 2,000 years, Chinese imperial astronomers carefully observed and recorded celestial events: comets, eclipses, meteor showers, supernovae, sunspots. They did this with remarkable consistency, creating a database of the sky that modern astronomers still consult when studying historical events. Why? Because in Chinese cosmology, the emperor ruled by the mandate of heaven. The sky itself legitimized his authority. Any unusual celestial event, a comet, an eclipse, a bright new star, could be interpreted as a sign that the emperor was losing the mandate, that his dynasty might fall. So astronomical observation was a matter of state security. The imperial astronomers had an enormous responsibility. Miss an eclipse? Predict one that doesn't happen? That could be seen as incompetence or even treason. This pressure led to meticulous record-keeping and sophisticated predictive techniques. Chinese astronomers developed their own cosmological models, independent of Western and Islamic traditions. They divided the sky into different constellations, mapped the planet's movements, and calculated eclipse cycles. In 1054 CE, Chinese astronomers recorded the appearance of a guest star that was so bright it could be seen during daylight for weeks. This was a supernova, the explosive death of a massive star. The remnant of that explosion is what we now call the Crab Nebula, still visible through telescopes nearly 1,000 years later. Strangely, this supernova seems to have gone unrecorded in Europe. Perhaps European skies were cloudy that summer, perhaps European astronomers simply didn't notice or didn't think it worth recording, but Chinese astronomers, with their culture of systematic observation, made sure it was documented for posterity. The Maya, architects of time. And in the Americas, the Maya were creating perhaps the most sophisticated calendar system in the ancient world. Mayan astronomers didn't have telescopes. They didn't have glass lenses or metal instruments. What they had were sharp eyes, incredible patience, and centuries of accumulated observations. From the tops of their pyramids and temples, Mayan priests tracked the movements of Venus with astonishing precision. Venus was crucial in Mayan cosmology. It was associated with warfare, and military campaigns were sometimes timed to coincide with its movements. The Mayan calculated the Venus cycle, the time it takes for Venus to return to the same position relative to Earth and the Sun, to within hours of the modern astronomical value. They did this without any mechanical aids, simply by watching the sky night after night, year after year, generation after generation. They also tracked solar eclipses, lunar cycles, and the movements of other planets. They developed multiple interlocking calendars, a 260-day sacred calendar, a 365-day solar calendar, and a long count that tracked vast cycles of time spanning thousands of years. This wasn't abstract mathematics for its own sake. It was deeply embedded in Mayan religion, agriculture, and social life. Time itself was sacred. The calendar told you when to plant, when to harvest, when to perform ceremonies, when to wage war, when to make sacrifices to the gods. The ruins of Mayan observatories still stand in places like Chichen Itza and Uxmal. Buildings aligned to track the solstices and equinoxes, windows positioned to frame significant astronomical events, architecture that served as both temple and telescope. The shared human impulse. What strikes me as we travel across these different cultures and time periods is the universality of it all. Human beings everywhere have looked up at the sky and tried to understand it. They've seen different constellations in the same stars. They've told different stories about the same planets. They've developed different calendars, different cosmologies, different explanations for eclipses and comets and the movement of the heavens. But they've all felt the same wonder, the same curiosity, the same need to make sense of the cosmos. In ancient Greece, philosophers debated the nature of the stars. In medieval Baghdad, mathematicians calculated planetary orbits. In China, imperial astronomers tracked comets. In the Yucatan, Mayan priests carved astronomical tables into stone. They were all, in their own way, doing the same thing, paying attention to the sky, finding patterns, passing knowledge to the next generation. They were all looking for answers to the same profound questions. Where are we? What is our place in this vast universe? What are those lights in the darkness? How does it all work? Let me tell you about a man who changed everything while trying to change very little. His name was Nicholas Copernicus. He was born in 1473 in the city of Torun in what is now Poland. He was a church canon, a comfortable, respectable position that gave him a steady income and plenty of free time. He studied law and medicine. He advised his bishop on administrative matters. He helped reform the calendar. And in his spare time, he tried to solve a problem that had bothered him since his student days. The problem was this. Ptolemy's system for explaining planetary motion, the system that had been accepted for nearly 1,400 years, was complicated. Too complicated. In Ptolemy's geocentric model, Earth sat motionless at the center of the universe. The moon, sun, planets, and stars all revolved around us in perfect circles. But there was a problem. The planets don't move in simple circles across our sky. Sometimes they slow down, stop, move backward, what we call retrograde motion, then resume their forward motion again. To explain this, Ptolemy had to add epicycles, circles within circles. Each planet moved on a small circle, which itself moved along a larger circle around Earth. And when that still didn't match observations precisely enough, he added more epicycles, and more. The system worked, in the sense that it could predict planetary positions reasonably well, but it was baroque, inelegant, increasingly complex. Copernicus, with his mathematical mind and his aesthetic sense of beauty in nature, felt there had to be a simpler explanation. So he asked a radical question. What if we're not the center? The sun at the center. Imagine the courage it took to even think this thought. For 1,400 years, every educated person in Europe, every astronomer, every philosopher, every theologian had accepted that Earth was the center of creation. It made sense. It felt right. When you stand on the ground, you don't feel like you're moving. The sun rises and sets, the stars wheel overhead, everything seems to circle around us. And wasn't that fitting? Humans were God's special creation. The entire universe was built for us. Of course we were at the center. But Copernicus imagined something different. He imagined that the sun, not Earth, sat at the center of the solar system. Earth and the other planets all orbited the sun in circles. Earth also rotated on its axis once a day, which explained why the stars seemed to move across the sky. Suddenly, everything became simpler. You didn't need all those complicated epicycles. Retrograde motion had a simple explanation. When Earth, moving in its orbit, overtook a slower outer planet like Mars, that planet appeared to move backward against the background stars, like when you pass another car on the highway and it seems to move backward relative to distant landmarks. The heliocentric model wasn't just simpler, it was more elegant, more beautiful. And to a Renaissance mind steeped in Platonic ideals, beauty was a sign of truth. But Copernicus was cautious. He knew how controversial this idea would be. He knew it contradicted Aristotle, contradicted Ptolemy, seemed to contradict common sense and even scripture. So he worked on his theory quietly for decades, sharing it only with a few trusted friends, refining the mathematics, checking and rechecking his calculations. He didn't publish his book on the revolutions of the heavenly spheres until 1543, the year he died. According to legend, he received the first printed copy of his book on his deathbed. Whether he ever truly saw it, we don't know. Tycho Brahe, the noble observer. For decades after Copernicus's death, most astronomers remained skeptical. The heliocentric model was an interesting idea, but it wasn't obviously better than the old geocentric system. It made similar predictions, it had its own problems. Where was the proof? Then came a Danish nobleman with a passion for precision. Tycho Brahe was born in 1546 into a wealthy aristocratic family. As a teenager, he witnessed a partial solar eclipse and was amazed that astronomers could predict such events. He decided to dedicate his life to astronomy, an unusual choice for a nobleman. Tycho had a particular genius. He was the greatest naked-eye observer in history. He built enormous instruments, quadrants, sextants, armillary spheres, all larger and more precise than anything that had come before. He established an observatory on the island of Ven between Denmark and Sweden, which he called Uraniborg, the castle of the heavens. For 20 years, night after night, Tycho and his assistants measured the positions of stars and planets with unprecedented accuracy. They didn't have telescopes yet. Those wouldn't be invented for another few decades. But Tycho's instruments and his meticulous methods allowed him to achieve angular measurements accurate to within 1 or 2 arc minutes, about the width of a coin viewed from across a football field. Tycho compiled the most comprehensive and accurate astronomical data that had ever existed. He observed a supernova in 1572, proving that the heavens weren't unchanging as Aristotle had claimed. He tracked a comet in 1577, showing that it moved through the space between planets, disproving the old theory that comets were atmospheric phenomena. But Tycho couldn't accept the Copernican model, partly for philosophical reasons, partly because he believed, correctly, that if Earth moved, we should see stellar parallax, a slight shift in the apparent positions of nearby stars as Earth moves around the sun. He looked for it with his best instruments and saw nothing. Stellar parallax is real, but the stars are so distant that it's far too small to see without telescopes and precise measurements. So Tycho proposed his own compromise system. The Sun and Moon orbited Earth, but the other planets orbited the Sun. It was a hybrid model that tried to preserve Earth's special position while accommodating some of the elegance of heliocentrism. It was wrong, but his data was priceless. Kepler, the mathematical mystic. In 1600, a young German mathematician named Johannes Kepler became Tycho's assistant. It was an unlikely pairing. Tycho was a wealthy, temperamental nobleman. Kepler was a poor, sickly Protestant living in Catholic lands, often on the edge of financial ruin, brilliant but difficult. They worked together for barely a year before Tycho died suddenly in 1601. But in that brief time, Tycho gave Kepler access to his life's work, decades of precise astronomical observations. Kepler became obsessed with Mars. Mars was particularly problematic for both the Ptolemaic and Copernican systems. Its orbit seemed especially irregular. Even with Copernicus's simpler model, you still needed some epicycles to make Mars's motion match observations. Kepler spent years, literally years, trying to fit Mars's orbit to perfect circles. He tried different speeds, different center points, different sizes. He filled notebooks with calculations, working by candlelight in his small house, often cold and hungry, while religious wars raged across Europe. Nothing worked. The circle just wouldn't fit. The predictions were always slightly off from Tycho's careful observations. Finally, exhausted and frustrated, Kepler tried something radical. What if planetary orbits weren't circles? What if they were ellipses? An ellipse is like a squashed circle, a shape with two focal points instead of one center. And when Kepler put the Sun at one focal point and calculated Mars's orbit as an ellipse, suddenly everything clicked into place. The observations matched, the math worked. This was Kepler's first law. Planets orbit the Sun in ellipses, not circles. He went further. He discovered that a planet moves faster when it's closer to the Sun and slower when it's farther away. And he found the exact mathematical relationship that described this variation. This was his second law. And then, after more years of calculations, he found a beautiful relationship between a planet's orbital period and its distance from the Sun. This was his third law, and it suggested that some fundamental mathematical harmony governed the entire solar system. He published these discoveries in books with titles like The New Astronomy and The Harmony of the World. He was convinced he had uncovered God's geometric plan for creation. He wrote with the passion of a mystic and the precision of a mathematician. But here's what's beautiful about Kepler. He followed the data. Even when it contradicted his philosophical beliefs, he wanted circles, not ellipses. Even when it was tedious and difficult, even when it took years of exhausting calculation, he kept working until he found the truth. His laws of planetary motion were exact, mathematical, and testable. They worked. They predicted planetary positions better than any system before them. They were proof that the Copernican revolution was right. The Sun was at the center. Earth was just another planet, following the same mathematical rules as Mars and Jupiter and Saturn. Galileo, eyes to the heavens. And then in 1609, everything changed again. An Italian mathematician named Galileo Galilei heard about a new invention from the Netherlands, the telescope. Someone had discovered that combining glass lenses in a tube could make distant objects appear closer. Galileo immediately understood the implications. He built his own telescope and then improved it, increasing its magnification from 3 times to 20 times to 30 times. And then he did something no one had done before. He pointed it at the sky. What he saw astonished him. The moon wasn't a smooth, perfect sphere as Aristotle had claimed. It was rough, cratered, mountainous, a world, not a heavenly light. The Milky Way wasn't a mysterious glow. It was composed of countless individual stars, far too faint to see with the naked eye, but revealed by the telescope. Jupiter had 4 moons orbiting it, tiny points of light that moved from night to night, clearly circling the giant planet. This was direct evidence that not everything orbited Earth. Here was a miniature solar system, visible to anyone with a telescope. Venus showed phases like the Moon, crescent, half, gibbous, full, which only made sense if it orbited the Sun, not Earth. Saturn looked strange. Galileo's telescope wasn't powerful enough to resolve its rings clearly, so it appeared to have ears or handles. But it was clearly different from other planets. Galileo published his observations in 1610 in a short book called Sidereus Nuncius, the Starry Messenger. It became an immediate sensation. Suddenly, astronomy wasn't just mathematical theory, it was something you could see with your own eyes. The evidence was there in the sky, visible to anyone with a telescope. But evidence doesn't always convince. Galileo's support for Copernicanism brought him into conflict with the Catholic Church. The Church wasn't inherently opposed to astronomical research, but Copernican theory seemed to contradict Scripture. If the Bible said the sun stood still for Joshua, didn't that mean the sun normally moved? Galileo argued that Scripture spoke in everyday language, not scientific precision. He believed that the Bible shows the way to go to heaven, not the way the heavens go. But church authorities were nervous. The Protestant Reformation was still raging. They didn't want Catholics questioning Bible interpretation. In 1616, the Church officially declared Copernicanism false and contrary to Scripture. Galileo was warned not to defend it. For years he obeyed, but in 1632 he published the dialogue concerning the 2 chief world systems, which compared the Ptolemaic and Copernican models. Technically, it was neutral, presenting arguments on both sides. In reality, it made the Copernican case overwhelmingly convincing and presented the geocentric defender as a fool. The Church felt betrayed. Galileo was summoned to Rome, tried by the Inquisition, and forced to recant his views. He spent the last years of his life under house arrest, blind and ailing, forbidden to publish on controversial topics. But the truth was out. The telescope had been invented. Anyone could look through it and see Jupiter's moons, Venus's phases, the mountains on our moon. The evidence was there in the sky, undeniable and revolutionary. The Earth moved. We were not the center. The old cosmos had died, and a new one was being born. The weight of the revelation. Try to feel what this meant, not just intellectually, but emotionally. For thousands of years, humans had believed we were special, the center of creation, the purpose of it all. The stars, the sun, the planets, they existed for us, moved for us, marked the passage of our time. And now, suddenly, we were just one planet among others, circling a star that was itself just one star among countless billions. Our solid, unmoving Earth was hurtling through space at tremendous speed. Everything we thought was permanent was actually in motion. Everything we thought was central was actually peripheral. Some people found this terrifying. It felt like a demotion, a loss of meaning. If we're not the center, what are we? If Earth is just one planet among many, are we cosmically insignificant? But others, perhaps you can feel this too, found it exhilarating. The universe.
In 1665, bubonic plague swept through London. The great city, crowded and dirty, was devastated. Thousands died. Those who could fled to the countryside. Cambridge University closed its doors and sent students home. Among those students was a young man named Isaac Newton, just 22 years old, recently graduated with an undistinguished degree. He returned to his family's farm in Woolsthorpe, Lincolnshire, a small manor house surrounded by fields and orchards. For the next 18 months, while plague ravaged England, Newton sat alone in the countryside and thought. What he thought about would change everything. The apple and the moon. The story of Newton and the apple is famous, perhaps too famous. It's been simplified, made into a cartoon. An apple falls on his head, he shouts Eureka, and invents gravity. The real story is more subtle and more profound. Newton was sitting in his mother's garden one day. This much seems to be true, when he saw an apple fall from tree. A common sight. Utterly unremarkable. Apples fall. Everyone knows that. But Newton asked a question that seems obvious in retrospect, but was revolutionary at the time. Why? Not why do apples fall in the sense of because they're heavy, or because that's their nature. Those weren't explanations, they were just descriptions. Newton wanted to know the actual cause. What force pulled the apple down? And then, and this is the leap of genius, he looked up at the moon. The moon doesn't fall. It stays up there, night after night, circling Earth endlessly. Why doesn't it fall like the apple? Or does it? Newton imagined the moon as a kind of projectile, like a cannonball fired from a very powerful cannon. If you fire a cannon horizontally, the ball travels forward while simultaneously falling toward Earth. Fire it faster, and it travels farther before hitting the ground. But what if you could fire it fast enough that as it fell, the curve of its fall matched the curve of the Earth's surface? It would fall and fall and fall, but never hit the ground. It would orbit. The moon, Newton realized, is falling. It's constantly falling toward Earth, but it's also moving sideways fast enough that it keeps missing. The same force that pulled the apple down pulled the moon toward Earth. The same force. This was stunning. It meant that the heavens and the earth obeyed the same physical laws. There wasn't one set of rules for celestial spheres and another for earthly objects. There was just physics. Universal physics. The mathematical universe. But Newton didn't stop with this intuition. He set out to prove it mathematically. He already knew Kepler's laws, those elegant mathematical relationships that described planetary orbits, but Kepler's laws were descriptive, not explanatory. They told you how planets moved, but not why. Newton needed a theory of force, a theory that could explain why planets move in ellipses, why they speed up near the sun and slow down far away, why the moon orbits Earth and Earth orbits the sun. He needed entirely new mathematics to do this. The mathematics that existed, algebra, geometry, wasn't sufficient for describing motion and change. So Newton invented calculus. Independently, a German mathematician named Leibniz invented it too, leading to a bitter priority dispute that would last decades. But that's another story. With calculus, Newton could describe acceleration, the rate of change of velocity. He could write equations that related force, mass, and motion. He could prove mathematically that if gravity decreased with the square of distance and pulled objects toward each other proportionally to their masses, then planets would naturally orbit in ellipses. Kepler's laws weren't arbitrary. They were consequences of deeper principles. It took him decades to fully work this out, to make it rigorous, to convince himself that it was correct. He was secretive, intensely private, reluctant to publish. Only the urging of his friend, the astronomer Halley, finally convinced him to compile his discoveries into a book. That book, Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, published in 1687, is perhaps the most important scientific work ever written. The Principia. Rules of the universe. In the Principia, Newton laid out 3 laws of motion and his law of universal gravitation. These laws were simple, elegant, and all-encompassing. Every object continues in a state of rest or uniform motion unless acted upon by a force. The acceleration of an object is proportional to the force applied and inversely proportional to its mass. For every action, there is an equal and opposite reaction. And gravity. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. That's it. 4 principles. And from these, you could derive the motion of everything in the cosmos. Why do planets orbit in ellipses? Newton's laws explained it. Why does the moon orbit Earth? Same laws. Why do the tides rise and fall twice a day? The moon's gravity pulling on Earth's oceans. Why do apples fall? Same force that holds the planets in their orbits. Newton had unified terrestrial and celestial mechanics. He had shown that the entire universe operated according to mathematical laws that could be written down, understood, and used to make predictions. The night sky was no longer a realm of divine mystery. It was a laboratory. A vast experiment in physics playing out across millions of miles that we could study and comprehend from our small world. And if we could understand the heavens, what else might we understand? What other mysteries might yield to reason and mathematics? This was the Enlightenment spirit, the conviction that human reason could illuminate everything, that ignorance and superstition could be replaced with knowledge and understanding, that the universe was knowable. It was intoxicating, it was empowering, and it set the stage for everything that would come next.
Let me tell you about a musician who became one of the greatest astronomers in history. William Herschel was born in Hanover, Germany in 1738. He made his living as an organist and composer in England, teaching music lessons, conducting orchestras, writing symphonies. It was respectable work, but not what would make him famous. His sister Caroline joined him in England, and together they pursued an unusual hobby. They made telescopes. Not just any telescopes. Herschel was obsessed with seeing deeper into space than anyone had before. He believed that with a large enough telescope, he could see farther and farther, discovering new objects, mapping the structure of the cosmos itself. But good telescopes were expensive, so Herschel decided to make his own. He cast his own mirrors, grinding and polishing them by hand. Tedious, painstaking work that took hours and sometimes days of continuous effort. Caroline would read to him while he worked or feed him bites of food so he didn't have to stop. They were driven by a shared obsession to see what had never been seen. A new planet. On March 13, 1781, while systematically surveying the sky with one of his homemade telescopes, Herschel noticed something odd. A small disk that moved against the background stars from night to night. At first, he thought it might be a comet, but as he and other astronomers tracked it over weeks and months, calculating its orbit, they realized something stunning. It was a new planet. A new planet. For all of human history, we had known 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, Saturn. The ancients knew them. Every civilization that looked up had seen them. They were the wandering stars, the limits of our solar system. And now suddenly there was a 6th, orbiting far beyond Saturn, taking 84 years to complete a single orbit around the sun, was a world no human had ever seen until Herschel pointed his telescope at it. He wanted to name it Gorgium Sidus, George's star, after King George III of England. Others suggested naming it Herschel after its discoverer. Eventually, continuing the tradition of naming planets after Roman gods, it became Uranus, the ancient god of the sky, father of Saturn. The discovery made Herschel famous overnight. King George gave him a royal pension, allowing him to quit music and devote himself entirely to astronomy. Caroline became his full-time assistant and collaborator, and would later become a distinguished astronomer in her own right, discovering several comets and compiling crucial star catalogs. But Herschel's greatest ambition was still ahead. He wanted to map the universe itself. Counting the stars. Herschel developed a technique he called stargazing. He would point his telescope at a small section of sky and count how many stars he could see. Then he'd move to another section and count again, and again, and again. Over years, he counted stars in hundreds of different directions, building up a statistical picture of how stars were distributed in space. What he found was remarkable. The stars weren't scattered randomly. They were arranged in a flattened disk, what we now call the Milky Way galaxy. Our sun was embedded in this disk, along with billions of other stars. When we look along the plane of the disk, we see vast numbers of stars appearing as the misty band of the Milky Way. When we look perpendicular to the disk, we see relatively few stars, looking out into the darkness beyond our galaxy. Herschel was mapping the geography of the cosmos. He was showing that the universe had structure, shape, architecture. He also discovered that many nebulae, fuzzy patches of light that appeared in telescopes, were actually clusters of countless individual stars, so distant they blurred together. He cataloged over 2,500 of these nebulae and star clusters. Some of them he realized might be separate island universes, galaxies beyond our own, though he couldn't prove it with his telescopes. Herschel was peering deeper into space than any human before him. He estimated that light from the distant objects he could see had taken millions of years to reach Earth. When we looked at the night sky, we were looking backward in time, seeing the universe as it was long ago. The night sky wasn't just vast in space. It was vast in time, too. The speed of light. But how did we know how fast light traveled? How could we possibly measure something that seemed instantaneous? The story begins with Jupiter's moons, those 4 points of light that Galileo had discovered in 1610. Astronomers had been tracking them for decades, timing their orbits with increasing precision. These moons disappeared behind Jupiter and reappeared on the other side with predictable regularity. They were like celestial clocks. In the 1670s, a Danish astronomer named Ole Romer noticed something puzzling. When Earth was closest to Jupiter, the moon's eclipses happened slightly earlier than predicted. When Earth was farthest from Jupiter, they happened slightly later. Why? Romer proposed a radical explanation. Light had a finite speed. When Earth was closer to Jupiter, light from the moons had less distance to travel, so we saw the eclipses sooner. When Earth was farther away, light had to travel the extra distance across Earth's orbit, causing a delay. He calculated that light took about 22 minutes to cross the diameter of Earth's orbit. This was remarkable, not just that he'd found a way to measure light speed, but that the speed was finite at all. Many philosophers had assumed light traveled instantaneously. Later, more precise measurements refined the number. Light travels at approximately 186,000 miles per second, or about 300,000 kilometers per second. It's incredibly fast by human standards. It can circle Earth's equator more than 7 times in 1 second. But on cosmic scales, even light speed is slow. Light from the sun takes about 8 minutes to reach Earth. Light from the next nearest star, Proxima Centauri, takes 4.2 years. Light from the center of our galaxy takes about 26,000 years. Light from the Andromeda galaxy, our nearest large galactic neighbor, takes 2.5 million years. When you look up at the night sky, You're not seeing the universe as it is now. You're seeing it as it was. Every star is a time capsule. The fainter and more distant the object, the further back in time you're looking. Herschel understood this. When he looked through his powerful telescopes at the faintest, most distant objects he could detect, he was seeing ancient light, light that had been traveling towards Earth for longer than human civilizations had existed. The night sky wasn't just a snapshot of the present. It was a museum of cosmic history.
Photography changes everything. In the mid-1800s, a new technology revolutionized astronomy: photography. Before photography, astronomers had to record their observations by hand. They would look through the telescope and draw what they saw, or write descriptions, or make measurements. It was tedious, subjective, and limited by human vision and memory. But photographic plates could capture light over time. Point a camera at a dim object, leave the shutter open for minutes or hours, and the faint light would accumulate on the plate, revealing details invisible to the eye. Suddenly, astronomers could see fainter stars, more distant nebulae, structures and details that had been completely hidden. They could create permanent records that could be studied and restudied, measured and analyzed. One of the pioneers was William Cronch Bond in America, who in 1850 made the first photographic image of a star. By the 1880s, astronomers were using photography routinely, building specialized cameras for their telescopes, compiling photographic star catalogs. This democratized astronomy in a way. You no longer needed perfect weather and a skilled observer's eye. The photographic plate didn't blink, didn't get tired, didn't suffer from subjective biases. It simply recorded what was there. And what it recorded was stunning. The Great Nebula Debate. By the early 20th century, powerful telescopes had revealed the night sky to be filled with strange, fuzzy objects, nebulae. Some looked like clouds, others had spiral structures, some were round and fuzzy. They came in all shapes and sizes. But what were they? Some astronomers believed they were clouds of gas within our own galaxy, perhaps regions where new stars were forming, or perhaps the remnants of old stars that had exploded or dissipated. Others believed they were island universes, separate galaxies far beyond our own, each containing billions of stars scattered through an unimaginably vast universe. In 1920, the Smithsonian Museum of Natural History hosted what became known as the Great Debate. Two prominent astronomers, Harlow Shapley and Heber Curtis, argued their cases before an audience of scientists and the public. Shapley argued that the spiral nebulae were within our galaxy, which he believed was enormous, much larger than most astronomers thought. Our galaxy, he said, was essentially the entire universe. The spiral nebulae were just nearby structures. Curtis argued that the spiral nebulae were separate galaxies, far outside our own. Our galaxy was just one of countless others, scattered through infinite space. The evidence was ambiguous. Neither side could definitively prove their case. They needed better telescopes. They needed better measurements. They needed someone who could measure the distance to these spiral nebulae. Enter Edwin Hubble. Edwin Hubble was a tall, athletic man from Missouri who had studied law at Oxford as a Rhodes Scholar before returning to America and, somewhat impulsively, deciding to become an astronomer instead of a lawyer. By the 1920s, he was working at Mount Wilson Observatory in California, home to what was then the world's largest telescope, a 100-inch reflector with unprecedented light-gathering power. Hubble was patient and methodical. He spent night after night photographing the Andromeda Nebula, the largest and brightest of the spiral nebulae, searching for individual stars within it. In October 1923, he found what he was looking for, a type of variable star called a Cepheid. These stars brighten and dim with a regular period, and crucially, astronomers had discovered that the period of variation was directly related to the star's intrinsic brightness. By measuring how long a Cepheid took to complete one cycle, you could calculate how bright it actually was. And by comparing that to how bright it appeared from Earth, you could calculate its distance. Hubble measured the Cepheids period, he calculated its true brightness, and he compared it to its apparent brightness. And he discovered that the Andromeda Nebula was nearly 1 million light-years away. Later, more refined measurements would increase this to about 2.5 million light-years. This was far, far beyond the boundaries of our own galaxy. Andromeda wasn't a nebula within the Milky Way. It was a separate galaxy, an island universe containing hundreds of billions of stars, comparable in size to our own galaxy, separated from us by an enormous gulf of empty space. The great debate was settled. Curtis had been right. The universe was vastly larger than anyone had imagined. Our galaxy, which had seemed to encompass everything, was just a local neighborhood. And beyond it, in every direction, were other galaxies, billions of them, scattered through space like cities of stars. The universe is expanding. But Hubble wasn't done. His next discovery would be even more shocking. He began measuring the spectra of distant galaxies, analysis of the light they emitted to determine their composition and motion. And he noticed something strange. Almost all galaxies showed a red shift. Their light was shifted toward longer, redder wavelengths. This was the Doppler effect, the same phenomenon that makes an ambulance siren sound higher-pitched as it approaches you and lower-pitched as it recedes. When a light source moves away from you, its light gets shifted toward the red end of the spectrum. The red shifts meant the galaxies were moving away from us. And the farther away a galaxy was, the faster it was receding. In 1929, Hubble published his findings. The universe was expanding. Not just some galaxies moving while others stayed still, but systematic expansion everywhere. The fabric of space itself was stretching, carrying galaxies apart from each other. This was revolutionary. It meant the universe had a history. If everything was flying apart now, then in the past, everything must have been closer together. Run the clock backward far enough, and you'd reach a moment when all matter was compressed into an infinitesimally small point. The universe had a beginning. This idea, which would eventually become known as the Big Bang theory, was controversial at first. Many scientists resisted it. An eternal, unchanging universe seemed more elegant, more philosophically satisfying. A universe with a beginning raised troubling questions about what came before, what caused it, what it might mean. But the evidence kept accumulating. The universe was expanding. The night sky itself was telling us that the cosmos had a history, a story, a direction. Looking back in time. Think about what this means for a moment. When you look up at the night sky tonight, you're not seeing the universe as it is now. You're seeing it as it was. The light from every star, every galaxy, left its source years or millennia or millions of years ago. It's been traveling towards you through the emptiness of space, carrying information about the past. The light from the sun left 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd keep seeing it, kept feeling its warmth, kept living in a world where the sun existed even though it would already be gone. The light from Sirius left 9 years ago. You're seeing it as it was when you were younger or before you were born. The light from the center of our galaxy left 26,000 years ago, when humans were just beginning to paint on cave walls and telling stories around fires. The light from Andromeda left 2.5 million years ago, long before modern humans existed, when our ancestors were Australopithecus, using simple stone tools, not yet masters of fire. And the most distant galaxies we can see with our best telescopes, their light has been traveling for over 13 billion years. We're seeing them as they were shortly after the Big Bang itself, when the universe was young and stars were just beginning to form.
The night sky is a time machine. Every direction you look, you're looking into history. The deeper you see, the farther back you go. And if you could see far enough, if you had a powerful enough telescope, you could look back to the very beginning, to the first moments when light could travel freely through space, to the cosmic dawn. The night sky isn't just above us, it's around us, through time and space. Every photon of starlight carries a story. Every distant galaxy is a messenger from the past. We are surrounded by history. We are bathed in ancient light. And when you understand this, really feel it, the night sky becomes something more than beautiful. It becomes profound. It becomes a connection to deep time, to the history of everything that exists. So how old is the universe? How long has this cosmic story been unfolding? For most of human history, this question had no scientific answer. Religious traditions offered various accounts. Some counted thousands of years. Others spoke of eternal cycles of creation and destruction. But there was no way to actually measure the age of the cosmos. That began to change in the early 20th century. Geologists, studying rock formations and radioactive decay, determined that Earth was billions of years old, far, far older than anyone had imagined. This gave evolution time to work, gave continents time to drift, gave mountains time to rise and erode away. But the universe itself, that was harder to measure. Hubble's discovery of cosmic expansion provided a clue. If you knew how fast galaxies were moving apart and how far apart they were now, you could calculate backward to find when they were all in the same place. The expansion rate, now called the Hubble constant, was like a cosmic clock running in reverse. Early estimates put the age of the universe at about 2 billion years. But this created a problem. The oldest rocks on Earth were older than that. How could Earth be older than the universe? The measurements were wrong. Hubble's distance scale was off. Other astronomers refined the measurements, corrected errors, recalculated. The estimated age of the universe grew. 5 billion years, 10 billion years, 13 billion years. Today, using multiple independent methods, including observations of the cosmic microwave background, the oldest stars, and the large-scale structure of the universe, we can say with remarkable confidence, the universe is approximately 13.8 billion years old. 13.8 billion years of cosmic history. And we, here on Earth, are part of that story. The cosmic calendar. The astronomer Carl Sagan once proposed a beautiful way to visualize this immense span of time. He called it the cosmic calendar. Imagine compressing the entire 13.8 billion year history of the universe into a single calendar year. January 1st at midnight is the Big Bang. December 31st at midnight is right now, this very moment. On this scale, what does history look like? January 1st happens on January 1st. For the first few minutes, the universe is incredibly hot and dense. Matter, as we know it, doesn't exist yet, just energy, quarks, fundamental particles in a state we could barely imagine. By January 3rd, the first atoms form, hydrogen and helium, the simplest elements. For months, nothing much happens. The universe expands and cools. It's dark. There are no stars yet, no galaxies, just vast clouds of hydrogen and helium drifting through the void. Finally, around January 22nd, the first stars ignite. Massive, brilliant, burning through their fuel quickly. When they die, they explode as supernovae, creating heavier elements, carbon, oxygen, iron, and scattering them into space. Around February 16th, Our galaxy, the Milky Way, begins to form. Billions of stars swirling together through gravity into a massive spiral. Spring passes, summer passes, galaxies collide and merge, stars are born and die. The universe grows, more complex, more structured. Not until September 2nd, more than 8 months after the beginning, does our sun form. A medium-sized yellow star in a quiet arm of the Milky Way, unremarkable among billions of others. Shortly after, on September 6th, Earth coalesces from the disk of debris orbiting the young sun, a ball of hot rock, molten, bombarded by asteroids and comets, gradually cooling. Life appears surprisingly quickly. By late September, the first simple, single-celled organisms emerge in Earth's oceans. They're barely alive by our standards, just chemicals that can copy themselves. But it's a beginning. For months on the cosmic calendar, though billions of years of real time, life remains simple. Bacteria, algae, single-celled organisms. The planet slowly transforms. Oxygen, produced by photosynthetic bacteria, begins to accumulate in the atmosphere. The sky changes from orange to blue. Not until December 16th, just 2 weeks before the end of the year, do complex multicellular organisms appear. The Cambrian explosion, suddenly, over a relatively brief period, life diversifies into an astonishing variety of forms. Jellyfish, trilobites, worms, strange creatures with no modern descendants. December 19th, the first land plants appear. December 20th, insects follow. December 23rd, dinosaurs appear. December 26th, the first flowers bloom. December 30th, around 6 a.m., the dinosaurs go extinct, wiped out by an asteroid impact. Mammals, which had existed as small, shrew-like creatures scurrying in the shadows, began to diversify and grow larger. And humans? Anatomically modern humans, people who would look just like us if you met them on the street, they don't appear until December 31st at 11:52 p.m., 8 minutes before midnight. All of recorded history, the pyramids, the Roman Empire, the Renaissance, the Industrial Revolution, the moon landing, the internet, happens in the last 10 seconds before midnight. Your entire life, from birth to this moment, is a fraction of a second on the cosmic calendar. The humility and the wonder. Does this make you feel small? It should. We are small. Cosmically, we're almost nothing. A brief flicker in deep time. A tiny species on a small planet orbiting an average star in a galaxy with hundreds of billions of other stars, in a universe with hundreds of billions of other galaxies. But here's the miraculous thing. We know this. We figured it out. We, tiny, brief creatures, developed minds that could comprehend billions of years. We learned to read the rocks, measure the stars, decode the light from distant galaxies. We built telescopes and particle accelerators and space probes. We sent robots to other planets and landed humans on the moon. We looked up at the night sky and asked questions, and we kept asking until we found answers. We are brief, yes, but we contain multitudes. We carry the universe within us, literally. The atoms in your body were forged in the hearts of ancient stars. the calcium in your bones, the iron in your blood, the oxygen in every breath, all of it was created billions of years ago in nuclear fusion reactions at the cores of massive suns, then scattered into space when those stars exploded. You are the universe made conscious, made curious, made capable of understanding itself. But I need to tell you something humbling. Despite everything we've learned, despite centuries of observation, decades of space exploration, the most powerful telescopes ever built, we still don't understand most of the universe. In the late 20th century, astronomers discovered something shocking. The visible matter, stars, planets, gas, dust, everything we can see, makes up only about 5% of the universe's total mass and energy. The rest is something else. About 27% appears to be dark matter, some kind of invisible substance that doesn't emit light but has gravity. We know it's there because we can see its gravitational effects on galaxies and clusters of galaxies. Galaxies rotate too fast to be held together by the gravity of visible matter alone. Something else, something dark, must be providing additional mass. But what is it? We don't know. It might be exotic particles that don't interact with light. It might be something even stranger. We can detect its effects, but we can't see it directly, can't touch it, don't fully understand what it is.